circuit. The main way we modeled this is we took a look at what happened. We went to the low level and take a look at what happened if a particle hits a transistor. And we can take a look at the CMOS transistor, because this is the technology that is mainly used with gates. And the main thing is each radiation will create a single event, as a single event transient pulse. We'll assume the worst effect is if this radiation hits the drain of the transistor, and that will cause the problems. It will generate this pulse that depends on the radiation parameters that will last for a certain amount of time. Based on this certain amount of time and how many stages I have on my calculation and the logic there, in logic masking, I can decide if this radiation is actually going to flip a bit or not. Is this flip is bit going to propagate through our circuit or not? How do we add the radiation model to the whole circuit? And probabilistic computing. You can take a look. This is an example of the whole circuit. All the probabilistic models are here in orange. They all have the same probability vector, and they all have the same radiation model that I just described. It's also here in them. And you just have to note that there's a control part. This is a control logic, and we will assume that this part is either radiation hardened and it's not probabilistic, because an error in the control part can be very, very costly and will change the run of the software. So we assume that the control part of the circuit is non-probabilistic, it is radiation hardened. It's our big part of the circuit that does all this computationally intensive calculations, that is probabilistic, and also has the radiation model on it. Taking a look at the results, first let me present this slide that has the figures. This was by the George paper again. And what we can see, what they use to estimate their energy is the percentage of correct outcome from their adder. So they add too many random numbers, and percentage of correct numbers that are greater than a certain number delta compared for two distributions. First one is this BIVAS, the biased voltage distribution, where the voltage is different for each bit. The other one is non-BIVAS, where all the voltage bits are uniform. Whereas this is for the BIVAS and non-BIVAS, and this is versus the energy consumed. We can clearly see that the BIVAS is better. One thing we found out while studying this paper, this V delta is not a very good indication because it can be application dependent. We could not figure out what was the actual number of delta, what were the parameters. So we had to investigate the parameters of the function, the effect of B delta, and this was part of our study. So when we simulated everything for our full circuit, and we can see here our B delta, our delta was 32. We have 16-bit numbers. And these 16-bit numbers, the maximum value we're actually getting for each pixel was only 8 bits, so 2 to the 56, two numbers. These are normalized energy savings here. And this is for the BIVAS and non-BIVAS, and we can see here this is actually different distribution for the BIVAS. It's the best fit distribution for our geometric function, and we can see that we achieve much better correctness, less energy savings, but much better correctness. It doesn't show that we have a great error result, so we decided to take a look at something else. Maybe there's something else that would be more suitable for application. So we decided to take a look at the error distribution. And with the error distribution on the x-axis, what we can see is the number of errors in each range that corresponds to the error between, we start from 2 to the 0, 2 to the 1, basically from the magnitude of each bit. By using our BIVAS and limiting it to the first 6 bits, we can see that we limited the magnitude of large errors compared to the non-BIVAS approach. We still have much larger errors, so we can limit those. So there's probably, this gives us an indication that it might work for something like stereo vision, where there's the amount of large errors is less and we don't use all the bits. And for the stereo vision, so if we added, we did this for over 8 image pairs, and we did all this calculation. We did this calculation for 8 image pairs, where we calculate the 2 windows. We can see in the x-axis again the percentage of good disparity values. Here our error value, delta, is 2. How many of those values are good versus our energy savings? So we can see that we have a good percentage of good numbers, more than 80%. Let's take a look at a little bit more close-up of how, after we combined our stereo vision with our circuit and how things work. In general, stereo vision, as I explained in the slide in the beginning, you have two images, one by the left and one for the right, and you have to calculate the disparity by comparing one window to the other and doing a sliding function. So these are our two original window pictures. This is the ground truth. The ground truth, where the color shows the depth. The ground truth means the actual depth of the image, the actual distances. So this is our ground truth result from the previous two images, and this is what we use to compare oral vision results with. Now this is a more interesting slide where we see some pictures. The first one here that we see, this is with full energy, means we didn't use any 5-bus, no more voltage. There's no voltage scaling, no probabilistic computing. This is with our 5-bus approach. And as you can see here, you can still see the disparities. We can still recognize the disparities. Not as good as we had before, but we can still recognize them. And my next slide actually shows things a little bit better, because you can see here the difference in the error. The difference in the error between the case when we ran the circuit with a full energy and we ran it with the probabilistic computing. Now the blue, this line shows the correct result with, and the green one is the error with the probabilistic computing. And we can see here, this is the dip is something that happens with stereo imaging and how it works, and you probably had something close there, so there was a dip there. And we can see how the error varies a little bit, and this is, it goes up. This was done again for 8 image pairs, but you're doing all the calculations over them. So we have large sums of the disparity. So this is how many disparities and how many the sum of absolute difference. You can see it was still within an acceptable range. So our conclusion that actually the result of probabilistic computing for vision crossing is acceptable if we keep the probabilistic computing to the least significant bits. If we did this for the least significant bits, got the right distribution, and since stereo vision doesn't actually can deal with using errors because there is filtering, there is different, not all the pixels might count. It was good for this application. For different might be good for other similar applications, and it's probably a very application dependent method. Some of our future work is simulating the circuit we had with larger number of images, different radiation methods. I mean, we did our simulation based on MATLAB, so it was very time intensive. So we can probably do a better simulation with C++, run it on a bigger computer. We can run much more simulation to see how it works with something like that. Investigating it with more different vision algorithms, probably something might be more computationally intensive. We can see what we can do. We can try to test the performance if we take the probabilistic out, the radiation out, and see how the circuit does on FPGA. Because right now, one thing that we showed here is a model for hardware that doesn't exist. This is just a big summary of our project. If you want more details, I'm sure that you can take a look at our report online. And thank you.